All right, so let's jump into this deep dive. We had a listener recently share a cool piece with us, and it was a kind of like a close-up look, a tour, if you will, of the cockpit of a 2000 Cessna 172 Skyhawk.
Oh, yeah.
But specifically, they were focusing on the steam gauge instrumentation.
Okay. Interesting.
Now, I know for a lot of our listeners, this might seem a bit old-fashioned, kind of a step back in time compared to, the shiny digital displays we see in all the big airliners and such.
Right, right.
But what we have here is really a collection of classic analog flight instruments.
Yeah, like the fundamentals.
Yeah. And our mission in this deep dive is really to get into the nitty-gritty of, what exactly these gauges are telling us, what vital information they're giving to the pilot, and, why this foundational technology is still so important, even as, the fancy glass cockpits are becoming more and more common.
I think it's a really good point, right? Because so much of modern aviation is built on kind of those building blocks, those fundamental instruments that came before it.
Exactly. So our source material here jumps right into what they call the, quote, classic six-pack.
Oh, the six-pack, okay.
Now, while that might sound like a refreshing beverage choice for some folks, in aviation terms, this refers to that standard arrangement of the 6 primary flight instruments. Can you maybe paint a picture of this layout, for our listeners and explain, why this particular configuration kind of became so universally adopted?
Sure, yeah. So picture, you're sitting in the cockpit of this Cessna 172, and right in front of you, you have this cluster of 6 instruments, and it's laid out in 2 rows, 2 columns.
Mm-hmm.
And so on the top row, you have from left to right, you have your airspeed indicator, then you have your attitude indicator, then on the far right, you have the altimeter, and then right below those, from left to right again, you have the turn coordinator, the heading indicator, and then the vertical speed indicator. So all those 6 instruments together in that arrangement, that's your classic 6-pack. And, the reason it became so universal, like why this particular layout is, over the years and decades, really, of aviation, this is the layout that pilots found to be most intuitive, in terms of just quickly being able to cross-check and see all the information they need.
Makes a lot of sense, a standardized mental model.
Yeah. And also, because it's so universal, it means that a pilot can go from, one analog aircraft to another, and the instruments are going to be in roughly the same place.
So that makes sense.
So it just reduces that workload, reduces that, that potential for confusion. It just makes things a lot smoother.
Yeah, reduces errors. Yeah.
Exactly.
Excellent. Okay, so our source here highlights that these 6 crucial gauges are kind of relying on 2 main underlying systems. Let's maybe just briefly touch on those before we actually go into each instrument individually.
Sure.
What are those 2 main systems that are feeding information to these 6 gauges?
Right. So the first one is the pitot-static system. And as the name implies, it uses air pressure, both the dynamic pressure of the air and the static ambient air pressure.
Okay.
And this system is used to power 3 of the 6 instruments: the airspeed indicator, the altimeter, and the vertical speed indicator. And so the way it works is you have this component called the pitot tube.
Yeah.
And that's usually located, on the wing or on the nose of the airplane, and it's facing forward.
Okay.
So as the airplane's moving through the air, that pitot tube is ramming air into it.
Oh, I see.
And then you have static ports, which are usually located on the side of the fuselage. And the static ports, they're not measuring that ram air, they're just measuring the ambient air pressure.
Makes sense. Okay.
And so by having those 2 different pressures, the pitot pressure and the static pressure, the instruments can then use that information to figure out things like airspeed, altitude, and vertical speed.
Really neat. Okay, so that covers half of them. What about the other 3 instruments?
Right. So the other 3 instruments, the attitude indicator, the heading indicator, and the turn coordinator, those are all gyroscopic instruments. So they rely on a spinning gyro to maintain a reference in space.
Mm-hmm.
And there's a couple different ways those gyros can be powered. The traditional way, especially in older airplanes, is using a vacuum system.
Okay.
So there's actually a vacuum pump that's mounted on the engine.
Wow.
And it creates suction, and that suction is used to spin the gyro.
Fascinating.
But some airplanes, more modern airplanes or airplanes with, maybe different systems, they might use an electrically powered gyro. But the important thing to understand is that, if that vacuum system fails or if there's an electrical problem, then those instruments can be affected.
Right. You lose that power source, and you could potentially lose those instruments. That's a good point.
Right, exactly.
Okay, so let's actually get into the specifics of each of these 6 instruments. Let's start with the airspeed indicator. Our source calls it the speedometer in the sky.
Makes sense.
It's located at the top left of that 6-pack that you described. So how does it actually measure the plane speed through the air, the airspeed?
Okay, so as we were talking about with that pitot-static system, um, the airspeed indicator, it basically measures the difference between the ram air pressure, which is that pressure of the air being forced into the pitot tube, and the static air pressure.
Okay.
Right. And so the faster the airplane is moving, the higher that ram air pressure is going to be. And so the bigger that difference between the ram air pressure and the static
All
pressure.
right.
And so that's what drives the needle on the airspeed indicator. The bigger the difference, the faster the airplane is going, the higher the airspeed.
Makes sense. Okay.
And it's important to remember that, it's not measuring speed over the ground. It's measuring speed through the air.
Right. It's the airspeed. Yeah.
Which can be different, right?
Yeah.
If you have a headwind, your airspeed might be lower than your ground speed and vice versa.
That's a great point. Yeah.
Yeah. So airspeed indicator, very important for understanding, how the airplane is performing aerodynamically.
Exactly. And I've always been fascinated by, the face of the airspeed indicator, the ASI. It has those really distinctive color-coded arcs. What do those actually tell the pilot at a glance? What are they communicating?
Yeah, those are super important. They give you those quick visual cues. So, if you're within the safe operating limits of the airplane, or if you're getting close to any limits.
Okay.
So the green arc, that represents your normal operating range. So most of the time when you're flying the airplane, you're going to be within that green arc. Then you have the white arc, and that indicates the flap operating range.
Got it.
And the flaps are those surfaces on the wings that you extend for takeoff and landing.
Right.
So basically, when you have the flaps down, you can fly a little bit slower.
Okay.
So that white arc is telling you, what speeds are safe to fly at with the flaps extended. Then you have the yellow arc, and that's kind of a caution range.
Gotcha.
So you can fly in the yellow arc, but you only want to do that in smooth air because if you hit turbulence, you could overstress the airplane.
I see.
And then finally, you have that red line.
Yeah, that one always catches your eye.
That's the never exceed speed, or VNE. And that's basically, the speed that you absolutely do not want to go above.
Yeah, that's the hard limit.
Because if you do, you could, potentially cause structural damage or even, a catastrophic failure of the airplane.
Yeah, not a good day.
Not a good day at all. So yeah, those colored arcs, super important to be aware of.
Absolutely. So in, kind of everyday flying of this Cessna 172, how would a pilot be referring to the airspeed indicator in the various phases of flight? How would they be actually using it?
Right. So, starting with takeoff,
Yeah.
as the airplane's accelerating down the runway, the pilot's going to be watching that airspeed indicator.
Okay.
And they're going to be looking for that needle to start moving. And then they'll call out, airspeed alive.
Okay.
And then as they continue accelerating, they're going to be looking for a specific speed called the rotation speed, which is the speed at which they start to pull back on the controls and lifts the nose off the ground. And in a 172, that rotation speed is usually around 55 knots.
Okay, 55 knots. Got it.
Yeah. And then once they're airborne, during the initial climb, there are certain airspeeds that they want to maintain to get the best performance.
Yeah.
So there's VY, which is the best rate of climb speed, and that's the speed at which you gain the most altitude in the shortest amount of time. And in a 172, that's about 74 knots.
Got it.
And then there's VX, which is the best angle of climb speed.
Okay.
And that's the speed at which you clear obstacles the most effectively.
Right.
So, if you have trees or buildings at the end of the runway, you want to make sure you're climbing at VX so you can get over those obstacles.
That's a good point. Okay.
And that's about 62 knots in a 172. And then once you get to cruise altitude, typically you're going to be flying at a speed within that green arc.
Okay.
And for a 172, that's usually somewhere between, 90 and 110 knots.
Okay.
And then as you start descending for landing, you're going to be reducing your airspeed. And as you extend the flaps, that airspeed's going to come down into that white arc.
Got it.
And then your final approach speed, which is the speed you're flying just before you touch down, that's usually around 65 to 70 knots in a 172.
Uh,
So yeah, the airspeed indicator, it's really used throughout the entire flight
Makes sense.
to make sure you're flying at the right speeds for the given situation and also to prevent you from stalling the airplane or overspeeding it.
Yeah, really crucial instrument.
Absolutely.
Okay, so moving on to the top center of our six-pack, we have the attitude indicator, which is often referred to as the artificial horizon.
Uh-huh.
Our source describes it as, showing the airplane's orientation relative to that actual horizon, the real horizon. How does this instrument, which is, driven by a gyro, how does it manage to give the pilot this fundamental awareness of where they are in space?
Okay, so the attitude indicator, it's basically a gyroscope that's mounted in a way that it can rotate freely.
Okay.
And it's spinning at a very high speed. And because of that spinning, it wants to maintain its orientation in space.
Okay.
That's called gyroscopic inertia. And so on the instrument itself, you have a miniature airplane. And that airplane is fixed. And then behind that airplane, you have a background that represents the horizon.
Okay.
And so as the airplane pitches up or down or rolls left or right, that miniature airplane stays fixed, but the background moves.
I see.
So it gives you a very intuitive visual representation of where the airplane is in relation to the horizon.
Yeah, I see.
So even if you can't see the real horizon outside, you can look at the attitude indicator and you know exactly which way the airplane is pointing.
Very helpful.
Yeah.
Okay, and what kind of markings do we see on the face of a typical attitude indicator?
Right. So you'll usually see some lines that indicate the bank angle.
Okay.
So, how much the airplane is tilted left or right. And those lines might be at like 10 degrees, 20 degrees, 30 degrees, and so on.
Got it.
And then you'll also have some tick marks above and below the miniature airplane.
Okay.
And those tick marks indicate the pitch attitude, so how much the nose is pointing up or down relative to the horizon. So those markings basically give you a quantitative, measurement of the airplane's attitude
Gotcha.
instead of just a qualitative one.
That's helpful. So when does this attitude information become super important for the pilot? What are some scenarios where this instrument becomes vital?
Right. So the attitude indicator is especially important when you can't see the real horizon.
Okay.
So if you're flying in clouds or if you're flying at night and there's no, lights on the ground to give you a reference, or even if you're just flying in hazy conditions,
Yeah.
you might not be able to see the horizon very well. And in those situations, the attitude indicator becomes your primary source of information about the airplane's orientation.
Really critical then.
Yeah, absolutely. And so, in those situations, you're constantly cross-checking the attitude indicator with your other instruments.
Right.
To make sure you're maintaining the correct attitude.
Yeah, and especially your other senses.
Yeah, exactly.
That makes a lot of sense. Okay, so next up in the top row, we have the altimeter, situated on the right.
Okay, the altimeter.
This one gives us that, very important information of altitude above sea level. How does it use the principles of that pitot-static system that we talked about earlier to measure altitude?
Right, so the altimeter, it works based on the principle that atmospheric pressure decreases as altitude increases.
Okay.
So the higher you go, the lower the air pressure.
Makes sense.
And so inside the altimeter, there are these things called aneroid wafers, and these are like little sealed capsules.
Okay.
They're very sensitive to changes in air pressure.
Okay.
And so as the airplane climbs and the air pressure decreases, those aneroid wafers expand.
Right at it.
And then as the airplane descends and the air pressure increases, the aneroid wafers contract.
Okay, so they're constantly adjusting.
Yeah.
Wow.
And that expansion and contraction is linked to some gears and levers that drive the needles on the altimeter. So that's how the altimeter shows you your altitude.
Really ingenious system.
Yeah, it's pretty cool.
Okay, so the altimeter has those clock-like hands that, when you first look at it, can be a little confusing, maybe, to interpret. How do we actually read a typical three-pointer altimeter? What are we looking for?
Okay, so a three-pointer altimeter has 3 needles, and each needle represents a different order of magnitude of altitude.
Okay.
So the shortest needle, it represents tens of thousands of feet.
Okay.
Then you have a longer needle that represents thousands of feet.
Got it.
And then sometimes you have a really thin needle that represents hundreds of feet.
Okay.
And so to read the altimeter, you basically just add up the values indicated by each needle.
Oh, okay.
So, if the thousands needle is pointing at the 2
Okay.
and the hundreds needle is pointing at the 5, then your altitude is 2,500 feet.
Okay, makes sense, yeah.
Yeah, so it's kind of like reading a clock,
Yeah.
except instead of hours and minutes, you're reading altitude.
That's a good analogy. All right, so in the real world, in a flight, how's a pilot actually using the altimeter during those different phases of flight?
Okay, so before you even take off,
Okay.
it's important to set the altimeter to the correct local barometric pressure.
Okay, why is that so important?
So the altimeter, it's measuring pressure, right? And it's converting that pressure into an altitude reading.
Okay,
But the relationship between pressure and altitude, it can vary depending on the weather.
got it, got
So
it.
if you don't set the altimeter to the correct local pressure, then your altitude reading might be off.
Right, you could be higher or lower than you think you are.
Exactly, exactly. And so, that's why it's important to get that pressure setting from air traffic control or from a weather report, and to set that on your altimeter using the Colesman window,
Okay.
which is this little adjustable window on the altimeter.
Okay, the Colesman window, yeah.
Yes. And so once you have that set, then, during the takeoff and climb, you're going to be watching the altimeter to make sure you're climbing at the right rate
Okay.
and to make sure you're leveling off at the correct altitude.
Got it.
If you're flying in the traffic pattern around an airport, there's usually a specific altitude that you need to maintain.
Oh, okay.
So you're using the altimeter to make sure you're at that altitude. And then in cruise flight, you're going to be assigned an altitude by air traffic control,
Yeah.
and you're going to be using the altimeter to make sure you're staying within, plus or minus a certain number of feet of that altitude.
Right.
So, if they tell you to fly at 3,000 feet, you want to make sure you're not going above 3,050 or below 2,950.
Okay, you have to stay within those limits.
Exactly, exactly. And then, of course, during the descent, you're using the altimeter to monitor your descent rate and to make sure you're leveling off at the correct altitudes.
Yeah, so crucial instrument for all phases of flight, really. Okay, so moving on to the bottom row of our six-pack,
Yeah.
let's start with the turn coordinator on the left.
Yeah, the turn coordinator.
Now, this one seems to be doing double duty, giving us two distinct pieces of information. What are those?
You're exactly right. The turn coordinator tells us two main things. One is the rate and direction of the turn. So how fast are we turning and which way are we turning? And that's shown by the little airplane on the instrument.
Okay.
And then two, it tells us about the coordination of the turn. In other words, are we slipping or skidding? And that's shown by the inclinometer, which is that little ball in the curved tube.
Okay, the inclinometer, got it.
So the turn coordinator uses an electric gyro that can sense both roll and yaw.
Got it.
So it can tell you both how fast the airplane is banking and also how fast the nose is moving left or right.
Really helpful information.
Right.
Okay, so as pilots, how do we actually interpret the movements of that miniature airplane and the ball? How do we understand what it's telling us?
So first, let's look at the little airplane. When you initiate a turn, the little airplane on the turn coordinator will bank in the same direction as the real airplane.
Okay.
Now, there are usually little tick marks on the instrument, and if the wingtip of the little airplane lines up with the first tick mark, that means you're doing what's called a standard rate turn,
Okay, a standard rate turn.
which is 3 degrees of turn per second.
Got it.
And this is the standard rate of turn that's used in a lot of instrument procedures.
Makes sense.
Okay, now let's talk about the inclinometer, or the ball. So this little ball is free to move in that curved tube, and it's affected by both gravity and centrifugal force.
Okay.
In a perfectly coordinated turn, the forces are balanced and the ball stays centered.
Right in the middle.
Right, but if you're slipping, which means you're not using enough rudder, the ball will move to the inside of the turn.
Okay.
And if you're skidding, which means you're using too much rudder, the ball will move to the outside of the turn.
Got it.
And the mnemonic to remember this is step on the ball. If the ball is to the left, step on the left rudder pedal. And if the ball is to the right, step on the right rudder pedal.
Step on the ball. Makes sense. Okay, and how does the pilot actually use the turn coordinator during different phases of flight?
Well, during flight training, it's really helpful for learning how to do those standard rate turns
Okay.
and how to make those turns smooth and coordinated.
Gotcha.
So that's really important. In everyday flying, you're constantly using the turn coordinator to make sure your turns are coordinated, which makes the flight more comfortable for passengers and also more efficient.
Yeah, that makes sense.
During takeoff, especially in a single-engine airplane, you need to use rudder to counteract the torque from the engine.
Right, okay.
And the turn coordinator helps you do that and keep the airplane going straight down the runway.
I see.
Another cool thing about the turn coordinator is that it can be used as the backup in case the attitude indicator fails.
Oh, that's
So if, for example, the vacuum system fails and you lose your attitude indicator, you could still use the turn coordinator to keep the wings level and make gentle turns.
that's really helpful. A good backup.
Yeah, it's a really important instrument for a lot of reasons.
That makes sense. All right, so next up in our bottom row, we have the heading indicator, also called the directional gyro, or DG.
Okay.
Uh, our source describes it as a more stable compass.
Yeah.
What makes it more stable than the traditional magnetic compass?
Okay, so the heading indicator uses a gyroscope, but this gyro is spinning in the horizontal plane.
Okay.
And because it's spinning, it wants to stay aligned with a specific direction.
I see.
And so it's much less affected by things like turbulence or acceleration, which can make the magnetic compass kind of bounce around and be hard to read.
Okay.
So the heading indicator gives you a much smoother and more accurate indication of your heading.
That's helpful, yeah. Okay, and how do we actually read the heading indicator? What are we looking for, and why do we need to realign it every so often?
Right, so the heading indicator looks like a compass, with the compass rows and numbers for each heading.
Okay.
Your current heading is shown by the number that's under a little marker at the top of the instrument.
Gotcha.
But the thing about gyros is that they can drift over time. It's called precession, and it's just a natural characteristic of gyros.
Right.
So you need to periodically realign the heading indicator with the magnetic compass.
Right.
And there's usually a little knob on the instrument that you can use to do that.
I see.
And it's really important to do that regularly, especially on longer flights, because if you don't, the heading indicator could become inaccurate.
Yeah, you could end up going in the wrong direction.
Exactly.
So it's a constant check and balance between the two instruments.
Right.
Okay, so how do we actually use this heading indicator in the various phases of flight?
Okay, so before you take off, you want to set the heading indicator to match the runway heading or the compass heading, so you know you're starting off on the right track. During the climb and en route phases of flight, you use the heading indicator to maintain the desired course.
Okay.
And especially if you're getting heading instructions from air traffic control, you're going to be referring to the heading indicator to make sure you're following those instructions.
Got it.
Now, unlike the magnetic compass, the heading indicator doesn't have any lag.
Okay.
So when you turn, the heading indicator shows you the new heading immediately.
Right.
And that's really helpful for precise navigation. And then in the traffic pattern, you use the heading indicator to make sure you're rolling out on the correct headings for the downwind, base, and final approach legs.
Okay.
So it's used throughout the flight for maintaining your desired heading and for navigating accurately.
Got it. Okay, so we've made it to our final instrument in the six-pack, the vertical speed indicator, or VSI.
Okay, the VSI.
This one's at the bottom right, and it
Yeah.
tells us how fast we're climbing or descending.
Right.
How does it do that using the static air system?
All right. So the VSI is also connected to the static air system, but there's a little trick to it.
Okay.
There's a calibrated leak inside the instrument.
A leak. That sounds counterintuitive.
I know, right? But it's how it works. So when you climb or descend, the static air pressure changes.
Right.
But because of that leak, the pressure inside the instrument takes a little bit longer to equalize.
Okay.
And that difference in pressure is what drives the needle on the VSI.
Oh, I see.
So if you're climbing, the pressure outside the instrument is lower than the pressure inside, and that makes the needle go up.
Okay.
And if you're descending, the pressure outside is higher, and that makes the needle go down.
Got it.
And the faster you're climbing or descending, the bigger the pressure difference and the more the needle deflects.
Interesting. So if the needle is above zero, we're climbing, and if it's below zero, we're descending. Our source mentioned that it's a bit laggy, this VSI. What does that mean, and how does it affect the pilot?
Right, so because of that calibrated leak, there's a little bit of a delay in the VSI's response.
Okay.
It doesn't show you the change in vertical speed instantly. It takes a few seconds for the needle to settle.
Okay.
So pilots learn to anticipate that lag and to interpret the trend of the needle's movement,
Got it.
not just the absolute value at any given moment.
So you're looking at the big picture.
Right, exactly.
Yeah.
But even though it's a little laggy, the VSI is still really important for establishing and maintaining a steady rate of climb or descent, which is especially important for instrument approaches.
Okay.
You know, when you're trying to follow that glide path down to the runway.
Right.
And it's most effectively used in conjunction with the altimeter to give you a complete picture of your vertical profile.
Makes sense. Okay. Now that we've gone through each of these instruments, our source gives a pretty helpful overview of, how pilots actually scan all these instruments during the different phases of flight. It sounds like it's a lot of prioritizing and cross-checking information.
It really is. A good instrument scan is one of the most important skills a pilot can develop, especially if you're flying in instrument meteorological conditions where you can't see outside.
Okay.
But even in visual conditions, it's a good habit to have because it helps you build a mental picture of what the airplane is doing and where it's going.
That makes a lot of sense. Can you maybe give us some specific examples of what this instrument scan would look like during those different phases of flight?
Sure. So before takeoff, you're going to do a thorough check of all the instruments. You're going to make sure the altimeter is set correctly, that the heading indicator is aligned with the runway, that the attitude indicator is showing level, that the turn coordinator is centered, and that the airspeed and VSI are both 0.
Okay.
So it's making sure everything is good to go. During the takeoff roll, you're primarily focused on the airspeed indicator.
Okay.
You're looking for that airspeed alive call, and then you're watching for the rotation speed. You're also cross-checking the attitude indicator to make sure you're rotating at the right pitch.
Okay.
And you're keeping an eye on the heading indicator and turn coordinator to make sure you're staying on the runway centerline.
Got it.
Once you're airborne and climbing, you're still watching the airspeed indicator to maintain the appropriate climb speed.
Okay.
But you're also watching the altimeter to track your altitude gain and the VSI to monitor your climb rate.
Got it.
And you're still cross-checking the heading indicator and turn coordinator to maintain your heading and stay coordinated.
Makes sense.
In cruise flight, your scan becomes a little more relaxed, but you're still regularly checking all the instruments. You're making sure the altimeter is holding steady, the VSI is at 0, the airspeed is within the green arc, the attitude indicator showing level, and the heading indicator is on course.
Okay.
And every so often, you're checking the magnetic compass to make sure the heading indicator hasn't drifted.
Right. Yeah.
During the descent and approach, your scan becomes more focused again. You're watching the altimeter to track your descent, the VSI to control your descent rate, the airspeed indicator to make sure you're not getting too slow, and the heading indicator to make any necessary turns.
Got it.
On final approach, you're really dialed in on the airspeed, the VSI, and the altimeter to make sure you're coming in at the right speed and the right descent angle.
Yeah. That sounds pretty intense.
It is, but with practice, it becomes second nature.
That's the key, practice.
Yeah. So the instrument scan is really